So today I'll be talking about forensic match information. And this could be a very technical talk with a lot of math and equations and small fonts, but all of that is in a document I wrote that's on our website in the information tab under report. So if you like that, it's all there. There's even measure theory in the appendix. That's not what I'm going to do today. I'm just going to talk about the ideas in a more general way with more pictures. Okay, so imagine we're in some forensic modality and we want to understand different objects. These objects have types. There are like 1 billion cars out there in the world. There are thousands of different types. For the purpose of illustration, I'm going to limit myself to just 3, red, green, and blue. And so there are these 3 types of cars out in the world, and suddenly a crime happens. There's a policeman blowing a whistle, shots ring out, and a car speeds by. Okay, so what happens is that there's an eyewitness, somebody who looks respectable, right, and reliable, whatever that means, eyewitness, and he says that it was a blue car. Definite, 100%. It's a blue car. There's nothing else it could be. All right, so now we have the concept of the word match. He sees a match. But this is a statistics meeting, so that doesn't mean anything yet. We have to start going somewhere with that. So there's a match of blue to blue, and we take a look at what does it mean to have a random match probability for any type of forensic modality as a way of understanding potential match error when there's a perfect match. So one way of understanding it is there's a probability P, which is the prior probability of what you might see if a car went by. This is just a different type. And those prior probabilities, shown in brown, are a 1/6 for a red car, a 1/3 for a green car, and 1/2 for a blue car. So this gives us a sense of how rare these different types are, what the chance of a coincidence might be. And this is the notion of, with a perfect match, that there's a random match probability. What's the chance that you saw this by coincidence? Well, in that perfect world, we can now move to a likelihood ratio, which in this perfect case is just the reciprocal, 1 over the random match probability. What the likelihood ratio is telling us is something about the strength of evidence. It's a surprise factor. It changes our belief from the denominator, which is the chance of a coincidence, P, the random match probability, up to 1, which is this complete match. And so here we see different potential likelihood ratios depending on what might be compared with. 6 for the red car, 3 for the green car, 2 for the blue car. In this case, it happens to be 2 because that's what our witness is claiming. And when we produce the car, here's the blue car, we're going to compare this blue car from the suspect with the possible types. So we have a likelihood ratio, which is 2, 1 over the RMP. So that's the case when we have certainty of match, but usually we don't have certainty. There's some uncertainty of the actual match comparison, the numerator, if you will, of the likelihood ratio. And so now maybe we have a different eyewitness, and this eyewitness says, this car was going by so fast. I know it's not red, definitely not red. Could have been green, could have been blue. I really don't know. So let's say that that person is giving just a statement. It could be one or the other. One's not more likely than the other. It's green or blue. So that uncertainty now leads us to probabilities. And if they don't really know, it's one or the other, let's give them a posterior probability of 1/2 of whether they saw the green car or they saw the blue car, based on the data, likelihood functions, updates, whatever. There's now a posterior probability. Say it's 0 for the red car, 1/2 for the green car, 1/2 for the blue car. After seeing the data, that's now what the belief is. So that's the posterior probability of this type based on evidence. Well, the likelihood ratio is still there for us. It handles uncertainty. But now that we have a numerator of a half or 0, and a denominator of whatever the coincidence or random match probability would have been, we divide the posterior probability Q, shown in blue, by the prior probability P, shown in brown. If you use some algebra and Bayes' theorem, you're about 3 lines away from the probability of the evidence given one hypothesis divided by the probability of evidence given the other hypothesis. But this is the form we're going to use here. And now it's expressing a strength in evidence, and you have a clearer notion of a change in belief. When it was definite, you went from the random match probability, the rarity P, to 1. Now we're just going to Q. Q could be more, it could be less. Let's see what it is here. Well, for the green car, it's 1/2 divided by 1/3, which is 3/2. That's the likelihood ratio. And for the blue car on the right, that's 1/2 divided by 1/2 is 1. That's what the likelihood ratio is. So now we have the likelihood ratio handling uncertainty and giving us a measure of evidence. This is all of the work that's involved of observing cars, getting statements, whatever, any other processing. This has now been reduced to a number. If somebody says it's blue, I saw the blue car, it'll be a likelihood ratio of 1. If we're comparing with the green car, it'll be 3/2. All of that work is now in one number. There are lots of cars in the world, over 1 billion out there, and thousands of types. And in forensics, you can have very complex representations of different data types. You may have a high multi-dimensional space. It could be a very unstructured set. So while we can put these probabilities, priors, posteriors, likelihood ratios, on each element of the set, or even continuously, it's difficult to handle. And in probability, all of that can be reduced to a distribution. And cumulative distribution, here I'll be showing a probability mass distribution. So the idea is sort of a conceptual dimension reduction, just down to numbers, one dimension. And we see here on the x-axis, here's the likelihood ratio, 0, 1, 3/2, as we saw on the last slide. And now we put a probability distribution, in this case the prior probability, associated with each car. If you have a lot of cars, they would superimpose, but essentially we're seeing a probability of 1/2 for the blue car with a likelihood ratio of 1, probability of 1/3 for the green car with a likelihood ratio of 3/2. It's the same data we saw on slide 9. We're just restructuring it so that the x-axis is the likelihood ratio, the y-axis is the prior probability. So we can go from all these types with probabilities on them to a one-dimensional distribution. What if we're interested in an error set? And that's what we're going to be talking about for the rest of the half hour. And we want to identify an error set. What if someone says it's a blue car, we're comparing a blue car, that's the evidence coming into court. On the bottom right, there's a blue car, it's being compared against all these types. The likelihood ratio is 1. So what's the chance that we might make a misidentification of an innocent car, whether it's another blue car or any other type of car that has a likelihood ratio greater than or equal to 1? Well, if we look at our likelihood ratios on the bottom row, 1 is greater than or equal to 1 on the bottom right, 3/2 is greater than or equal to 1. So the set of cars here are the two on the right, the green and the blue. They have likelihood ratios that exceed that of the suspect car, the car that we're making the comparison with. And so that identifies an error set, an extreme set. This is the set of all types. Here there's 2 of them. You could have trillion of them with DNA, where the likelihood ratio on this set, on these objects, on these cars, these genotypes, whatever they happen to be, exceeds that of the comparison type. And a generalized random match probability adds up all the prior probability, all the coincidence probability on that extreme set. So this is the set where the evidence is at least as strong as it is for the blue suspect car. And here you'd have 1/3 for the green car plus a half for the blue car, it would add up to 5/6, and that would be the RMP. Reducing it to a distribution, we have the same distribution of likelihood ratios on the x-axis and prior probabilities on the y-axis. It's the same bar graph, and now we're asking, what is the tail of the distribution greater than or equal to 1 on the x-axis? And here we have 1 and 3/2 as the numbers of likelihood ratios greater than or equal to 1. And the prior probabilities are a half and a third. We add them together. Instead of looking at the whole set, we collapse them onto a real line, and we get 5/6. So this is a concept of a general random match probability, which I'm going to show you how it's used in DNA mixture analysis. And the notion, it's a way of measuring an error for someone who's interested, maybe a juror, of what's the chance I might be making a mistake. And so here are some properties that would be good for such a statistic to have if we're using it as an RMP. With probabilistic genotyping, you can do a thorough Bayesian probabilistic inference, and you can separate out each genotype. So now we can make a comparison of a separated genotype or a separated type from a mixture against a reference. We can do, as I'll show you, it's instantaneous calculation with prior and posterior probabilities at a locus to quickly come up with a distribution and then calculate this extreme probability. We want, relative to the matching type for DNA as genotype, that this extreme set of types that exceed a certain evidential force contains the matching genotype. We want all the LRs, the strength of evidence, to be as strong against every element in that set as against the matching genotype. We also want minimality. We want the RMP, the sum, to be the smallest possible sum that contains the matching genotype. We want it to reduce to the classical case of certainty when there's a singleton set. If there's only one genotype or one type in the set, it should just become RMP again. And we wanted to convey the chance of a false positive for an innocent person. And so this generalized RMP over an extreme set does all of that. So that's what I'll be continuing to talk about and how it works. And so you just replaced cars with genotypes. So there's maybe only 1 billion cars, but we know there's a trillion genotypes. With the new kits, there's a trillion genotypes. And all the math goes through. You start off with prior probabilities, shown in brown, little p, of what the priors would be on each genetic type. You do your statistical inference and separate out those genotypes and apply, get probabilities for each type, say at each location. And then you can construct a likelihood ratio for every possible one of the trillion genotypes by taking a ratio of posterior to prior. This is of course, the posterior is because of data, and now you have likelihood ratios, the same examples, 3/2 and 1. You can do exactly the same mathematical collapse. It's called a push-forward function in measure theory. You take all of these measures on the set, reduce it to a distribution, and here we have the likelihood ratios now shown in gray on the x-axis. We have probabilities of what these different types would be, but we don't care about the types anymore. They've been reduced to numbers. The chance of a likelihood ratio of 1 or of 3/2. We're going to take logarithms for reasons that'll be clear in a second. And so on this scale, we have numbers like 0 and 0.176. On a log scale, this is the log LR Locus distribution. So a computer can calculate this pretty instantly if it has the prior and posterior for a locus. But we want to combine independent tests. We want to get the full distribution. And the way that can be done is if you take the log of the likelihood ratio, by independence, on the first line, the likelihood ratio is a product of the likelihood ratios of different tests, LR1 times LR2 times LR3. The log of a product is the sum of the logs. So now we have the sum of log LRs. But importantly for probability distributions, the distribution of independent sums is the convolution of their distribution. Something, again, that can be done in a computer in a few milliseconds. And so you get an essentially instantaneous calculation of the distribution of what the likelihood ratios look like, say, for under the prior assumption of what's the chance that this is a random person. So here's an LR distribution calculated from that sort of convolution of these separate functions. And the likelihood ratio here is the strength of evidence for a particular genotype. The x-axis is the log LR. This is probability density vertically. And a particular person, shown in green, would have some LR value that falls along that axis. This is giving a strength. And now, instead of finding and adding all these extremal sets, all that's been reduced to a one-dimensional distribution. So we can now look at the area under the curve, the tail probability of the random match probability, which is what is the chance of error? What's the chance that an innocent person has the same or greater evidence against them as the defendant? And so that's how this random match probability is being used. So here's a case example from a recent case in Pittsburgh. There's a homeless man. He abducts a woman, throws away her phone, threatens her. She follows him because she's fearing for her life. But once they get to a crowded area across from a hotel, and he tries sexually assaulting her again, she screams. People chase after the man, and he's apprehended a few blocks away. With mixtures, crime labs generally don't do very well these days, using older methods. So our county crime lab, they got the evidence, they developed the data, and using their interpretation methods on most every item, they said that no conclusion can be made, insufficient data, it's too complex, and they didn't report match statistics, which is how we get the case. We do free screening on everything, so we've done over 60 cases, prosecution and defense in our county, and then we get it and we run a validated computer program on it, TrueAllele, and usually there's results there because most of these inconclusives, which is most of what the labs do on mixtures, are actually quite informative. So here are 4 evidence items: rectal swabs, non-sperm fraction, sperm fraction, hand, fingernails, right and left, all from the victim. And here's the log LRs that are found by computer. 15 zeros is a quadrillion, 30 zeros is a non-million. So a lot of information in these inconclusive mixtures, consistent with the victim and the suspect. Ultimately, based on a lot of evidence, including DNA, the gentleman did plead guilty. But what I want to focus now is on a smaller match statistic, this number that's 3.69. It's around 5,000 in actual numbers, and see how these ideas apply to a small match number and how we can understand it. This is a TrueAllele screenshot, but it's showing for one locus D16 these ideas. Out of the 100 possible allele pairs, what we're seeing is where there's more probability in the posterior distribution after having seen the data for maybe 15 allele pairs at a 95% credible level. The brown is showing the prior probability. This is what will enter into a random match probability. The blue is the posterior probability. And each of those are a separate distribution, and there's a lot of information before in these genotype distributions before you even compare it with someone. In this case, the defendant had an 1113 genotype that's circled in red. You can see that the ratio Q over P, posterior to prior, blue over brown, is around 3. And on a log scale, we see this when we look at all of the locus log LRs. The log LR circled in red again, and log of 3 is around 1/2, which is where the scale is on the right. So on I think there are 22 markers here. You see most of the weight of the evidence is tilting toward the defendant. There's some other loci that are non-informative or even a little bit of evidence the other way. You add up all the logarithms, take 10 to the power, and now you can make an evidence statement. There are many ways to state the likelihood ratio. You use Bayes' theorem. There's about 10 forms that I know of. But if you're working with separated genotypes, so you're comparing one genotype from a mixture to a reference genotype relative to a random genotype, then this statement just comes out of the math when you're comparing with one person, a definite genotype. And it's a match between the rectal swabs and the defendant is 4.89 thousand times more probable than a coincidental match to an unrelated person in some ethnic group. Okay? And so that's the statement you'd make about the strength of match. That's the evidence. From those prior and posterior distributions, convolving them all together from the loci, you can get several distributions. If you weight it according to the posterior probability, you'll get the contributor distribution. The x-axis is log LR. The vertical axis is probability density for that sample. There's a lot of information in a contributor distribution. Here's one thing, the Kullback-Leibler, the KL statistic here, is not very large. It's less than 1. The KL statistic is the expected value of the log LR. It's also a measure of divergence between the prior and the posterior probability distributions. So typically, if you look at this probability distribution, a likelihood ratio, when you compare it with someone, would be somewhere towards the middle. It wouldn't be that informative. It could even be exclusionary. In this case, though, the LR, which is over 3 log units, is far to the right. So this is a case where this question of what an RMP is might be more interesting. So let's take a look at the non-contributor distribution. This is the prior probability weighting. As we saw before, these are the log LRs weighted by prior probability of coincidence. And as it has to be, it's to the left of 0, that dashed line. By some math, it's always to the left. This is how it's distributed. So it's not that exclusionary either. Its average, its expected information is around 1 over 10, negative 1. But if you take a look at where that LR is falling, it's all the way to the right. And it looks like that tail probability in this case, on this evidence, not in a large-scale validation with hundreds of samples, this one case may have a small RMP. Well, we don't care if it's big or small. We calculate it. And the error statement for the RMP, this generalized RMP, answers a question. Here's the question. What's the chance that someone who didn't contribute their DNA to the rectal swabs has a likelihood ratio of at least 5,000? That's the question. And the answer is, because we calculate it, because once you have the distribution, you can instantly calculate the right tail, is that it's about 1 in 28 million. So in this case, on this data, with this comparison and that defendant, it turns out that it would be very rare for someone else to have that profile. Other people have looked at RMP methods. They've called them other things. They go by a lot of names, tail probabilities, p-values. Some people have approximated the LR distribution. There's been Monte Carlo simulations on small sets of genotypes, branch and bounds on larger sets, divide and conquer. Some people advise don't ever report an error measure. Other people prefer to always give the error estimate as equal to 1 over the LR. Okay, that's an approach, but it could be helpful to a trier fact. In this case, the RMP is much less than 1 over the LR. Let's see why. If you want the details of the math and these integrals, look at the paper. But starting from the top left, the random match probability is equal to the sum, the cumulative sum over the right tail of the contributor distribution divided by ALR, the average LR of the non-contributor tail. It's just a fact. And then if you write what's in those different terms, and you multiply by LR and divide by LR, which is the smallest value on that extreme set, you have 1 over the LR times the LR over the average LR times this cumulative sum. The two terms shown in red on the right line, each has to be less than 1, because a minimum LR over the average has to be less than 1, and a partial sum of probabilities is going to be less than or equal to 1. In this case, what do we see? The LR itself is about 1 in 5,000. That's the 4893. The second term is 1 over 2.4. And the third term, because the LR so far to the right on the contributor tail is about 1 over 2,500. When you multiply the two red terms together, you get roughly, say, 1 in 5,800. So you get a shrinkage of the 1 over the LR, that 1 in 5,000, by another factor of 1 over 6,000, and you end up with an RMP. The chance that an innocent person has a match statistic that high on this data of around 1 in 28 million. Okay? And again, for the math details, you can take a look at the paper. People have written about this in statistics and the law as a concept. Again, they don't call it RMP. People have said in statistics that you can view this error, or the RMP, as a probability of observing misleading statistical evidence, and that evidence and uncertainty are different. The likelihood ratio summarizes evidence. The RMP is measuring some sort of uncertainty. There have been law papers written by people about this, talking about an initial presumption of innocence, what a juror might be believing is a null hypothesis. Accreting more evidence might increase a likelihood ratio. I think p-value is a terrible word here because it has so many other meanings for hypothesis testing that have nothing to do with this. It's just a right tail. But that's what probability, that's what people have called it. And so it's a probability on a critical set of extreme LR values. And once that value gets smaller and smaller, then, as some legal scholars have said, this can help reduce error beyond reasonable doubt. And these questions of presumption of innocence, having more evidence and making probabilities smaller beyond reasonable doubt are juror issues. So in conclusion, the likelihood ratio summarizes DNA evidence. This generalized random match probability, which is for all extreme genotypes that exceed the defendant's LR or a tail probability, gives an error probability. Once it's a probability and it's not an LR, there's a lot you can do with it. It's a probability. You can multiply it by a population size, for example, and estimate in a city, say the size of Pittsburgh, that maybe has 2.8 million people, that the chance that you'd match an innocent person, if you want to do the math, it's small, right? It's maybe 1/10. With the same evidence, is the evidence as big as for the defendant? And remember, in other cases, that number could be very close to 1 over LR. In other cases, it can be very far. That's why you need to do the calculation. In fact, the likelihood ratio summarizes evidence. The random match probability is a way of understanding error or making a mistake. And they can both help a trier of fact to understand DNA evidence. As I said, the manuscript for this report is on our website. The slides for this talk and the handout are also on our website now, and there's a lot of information about DNA identification science. Thank you very much.